we also talked about the backward Euler scheme, which is instead of evaluating the derivative at the current time, you evaluate the derivative at the future time. So in other words, the only difference between the forward Euler and backward Euler was this. And remember, we talked about this as problematic a little bit because, you know, okay, how do I get my solution in the future? I have to solve an AX equal to B problem. But fine, let's separate that for the moment and just say, is this scheme stable if I were to iterate on it? Okay, that's the only change. And then when we go through this analysis, let's go back right through here. It's right here. Sitting right here is everything we need. And the only thing that changes is that these are not G of M's anymore. They're G of M plus 1s. Oh, you know what I'm going to do? Sweet. Okay, ready? It's almost like I planned it, but I totally just thought of it, and it could fail. But let's just go with it. Colors. Okay, ready? All right, so you will see how this calculation carries forward. I have a plus 1 here, and a, yeah, let me get that plus 1 there. Okay? Now, I still want to divide by, there's G of M plus 1, G of M plus 1. I still want to divide by G of M. It's going to cancel that one. I'm going to be left with a G here. I'm going to be left with a G here. That's okay. I'll just pull it right out. G. It's not my phone. Do you want me to answer that, Will?
Go ahead. You're a G.
Well, no, I'm not. I thought maybe it was you calling me. All right, I'm not going to answer it. I got time. I got time for you, Will. I don't got time for them. Calling the wrong number. Hey, hello. Okay. All right. There we go. Boom, boom. You see that G following around there? Okay. Everything's the same. G just keeps popping up. There's that G again. And now there's a G sitting there. So now I can't just take the absolute value. You see the G there. I still have to solve for this. So I can bring this over. Right? So let's continue now the calculation over here. So I have to move this to the other side, and I get G 1 minus I lambda sine. That's what I get. Or G is equal to 1 over 1 minus I lambda sine theta h. Take the absolute value of that. And there it is. Now, let's do the same thing we did before. There's your lambda. I have 1 over 1 plus something positive, so this is a little bit bigger than 1. Has to be. Everything's squared. Everything's real. 1 over something bigger than 1 is less than 1, which means if I iterate on this thing, my G is less than 1. If I take G to the mth power, M goes, in fact, this thing goes to 0. Scheme is stable. Okay? By the way, it's stable no matter how I pick lambda. Does it care? No. That phone, you're going to take a bat to it? I don't know. Somebody's calling.
You know who it is?
Who's that?
It's AK's class.
Oh. Oh.
He actually takes incoming calls.
Oh, he does? Should I take incoming calls?
No.
Oh, okay, good. All right. All right, sweet. Hey, what's up? What's up? Okay. Okay. All right. We can take incoming calls. Yes, this is the Applied Math Hotline. How may I help you? Oh, that sounds like a hard problem. Wow. Okay. Good luck with that. We get a 10th call. We could win T-shirts and stuff. It'd be awesome. All right, 2 schemes. Stable, unstable. These are a little bit odd in the sense that most schemes don't have sort of unlimited stability or no stability, right? So forward Euler, backward Euler, but you can see the difference. And all it was is this thing here. Now, and the thing I want to point out is when you look at this scheme here, right, it looks almost exactly the same. It's just this little thing. How harmful can that be? It makes all the difference in the world. Okay? So it's very deceptive to say, well, if I just change my scheme a little bit, oh, be careful. I just changed my scheme a little bit, and I went from always working to never working. Okay? Have that in mind in your head when you do this. All right, now let's keep working on this scheme and look at some of the other ones we came up with. All right, so let's go through and talk about, for instance, Lax-Winthrop. Now, Lax-Winthrop had the following scheme, and this will illustrate a little bit more clearly how, you get something that can work in certain regimes. And remember with Lax-Winthrop, what we did, we actually, hold on a second, let me write it all out. Okay. It's a lot like the Ford-Euler, except now we added this diffusion term. Remember, we just took a function u. You evaluated t plus delta t. We did a Taylor expansion up to, if you span around t plus delta t, you get derivative terms out. You get a ut, utt, and then you plug in your equation into it, and you get this thing out here. And it's kind of like a little bit of numerical diffusion. And then it kind of saves you in using your it's a correction to the Euler scheme that saves you by adding sort of this diffusion. So let's go ahead and go through the analysis again now. So, because I think just seeing it twice is not nearly enough fun, what we would like to do is see it multiple times, over and over again, so that you'll love von Neumann at the end of the day. Okay? Is everybody loving von Neumann yet? See, no hands went up. That means I got to do more. See how much you could have saved yourself? You could have said, yeah, I love him, and you're jumping up and down. I would have said, oh, sweet, okay, we'll quit now. But no. The love isn't there, and I can see it. I can see the love's not there. So let's go get some love for von Neumann. I have my g of m plus 1 over here times this e to the I c of nh. Left-hand side again, g of m. Same kind of terms here, right? You get this g of m, e to the I c of n h minus g of m, e to the minus I, plus. Here you get, again, g of m. And notice that everybody, these are n plus 1s here, n minus 1 there, n plus 1, h minus 2, g of m, e to the I, c of n, h, and then plus e to the, g of m, e to the I, c of n minus 1h. Boom, you throw it all in. Notice, everybody's got a g of m running around. This one has a g of m plus 1, so we can do what we did before. Divide by g of m. The only thing that's going to be left over is a g over here on this left side. Okay? One second, we're going to start. G. That's a good start. Okay. Now, I can also multiply through by e to the minus I c of nh. It's going to cancel this one, and that one. And then give me some differences for the others. So this here is going to be, I've already divided by g of m. I've multiplied this by e to the minus, so this is going to be all 1 here. That's going to go away. So you're going to get g is equal to 1 plus lambda over 2. And then what you get in that is you're going to get your e to the I, c of n plus 1 minus c of n, h, minus e to the I, c of n minus 1 minus c of n, h. That comes in from that term. Plus lambda squared over 2. Right? And then you have here e to the I, c of n plus 1, minus c of n, h. And I'm going to rearrange terms slightly here. You're going to get a plus e to the I, xc of n minus 1 minus xc of n h minus 2. The minus 2 comes because you have a g of m and you have e to the I. They all cancel out. This is what you get. Fairly clean. Okay? Once again, you assume that your xc of n are n zeta. Okay? And if you do that, then this becomes e to the I n zeta minus e to the minus I n zeta. Okay? E to the I n zeta minus, actually, sorry, zeta h zeta minus I h zeta. The ends cancel. You get this? That's our sign again. Plus lambda squared of 2. Same thing here. Now you get e to the I h zeta plus e to the minus I h zeta. And what's that? Cosine. Yeah. Great. I like when things show up that we know. So I need to get a 2i in here, right? So if that's a sign, I have to bring this 2 in. So let's bring the 2 in here. And then I can bring an I and an I. I'm going to bring this 2 in here. And that's going to make that a 1. Okay? So at the end of the day, you get g is equal to 1 plus I lambda sine h zeta plus lambda squared cosine h zeta minus 1. And by the way, what is cosine minus 1? There's another way you can think about writing that, and by using your trig identities. And that's basically going to give you, you can write this as, if you remember your half angle identities. Do you remember those? Yeah? I remember, you know, back in high school, junior year, do you guys remember making a 3x5 card? Or maybe it was just my high school. Everybody had their 3x5 card with all their trig identities on it. Half angles, double angles, with sine and cosine relationship, you know, cosine, 1 over cosine. You know, all that stuff was there. You didn't have this? This generation survived. Cynthia had it. You had that, right? 3x5? Oh, come on. The rest of you? You're just not good students? Just didn't, I don't care. 3x5, that's for losers. Okay. Anyway, I kept it all the way through college. Still use it. It was all in my little notebooks. I pulled it out pretty often. So, and you know what? It came in handy because right here I could just say, oh, I recognize that because I have my little table. That's a sine of half the angle, sine squared of half the angle. Okay? So when I do this, this becomes sine squared h zeta over 2, and there's a factor of 2 out front of this thing. Right there. There's my formula. A little bit more complex than before. Right? I mean, I got lambdas running around, and unlike previously, it's maybe not going to be so easy to see where this is bigger than 1 or less than 1. So let's go ahead and figure out the absolute value of that thing. If you take the absolute value of that thing and say, okay, what is then this? This is the quantity that's the only thing we care about is the absolute value of that thing. And in fact, I'm going to write down the absolute value squared. You have a real and imaginary part there, and what you're going to get is the following. Lambda to the 4th, 4 sine 4th zeta h over 2 plus lambda squared sine squared zeta h minus 4 sine squared zeta h over 2 plus 1. Okay. You have a 4th order polynomial in lambda to the 4. Right? This is going to be some quartic function. So, look, I can generically draw some quartic function. And of course, it looks like Husky W. Put up your dubs. That's not, you know, we went from gang symbols to now this is like how you go to the football game here. Have you seen that? Yeah, no, they got all the T-shirts made up, and you're supposed to all just do that. Yeah, whoa, yeah, go Huskies. Okay. Can you guys do that? Because I think they're going to kick you out if you can't. I don't know. I think that they're going to implement that policy. I'm just saying practice, okay? It's not that hard. But there you go. You get something like this. Why? Because that's positive. Notice, what do you care about? What you care about is this thing being bigger than 1. So there's a line here. That's 1. And notice right away, because this is positive, you know you're going to go above it at some lambda. Call it lambda c. So it's going to already tell you that I can take step sizes up to a certain point, and after that point, that thing is bigger than 1. I go unstable. That's all you care about. Okay? So it will be a range. You are allowed to take lambda values in here. That determines your CFL condition. Okay? So now this is a more realistic case. Complicated form. It's not that complicated, right? You can find. I never did. I don't know what the number is, but you could totally do it.